Hello everyone. So today we will learn mole concept. This will be part of a fundamental series which I'll be covering the next few lectures. Before we start the core of this channel, which is learning about biology and its applied subjects such as biotech, biochemistry and so forth. My target students would be from class 10th, 11th, 12th, or if you're preparing for a competitive exam, or you just are in different stage of your scientific career and need a refresher for mole concept. Now, why we need to understand mole concept, right? Now, as we know that all chemical reactions take place in their stoichiometric proportions. So what I mean by stoichiometry is that each reactant component have a certain proportion in which they react. For example, what you can see here is two hydrogen atoms react with one oxygen atom and form one molecule of water. If a number is not written here, that means the number is 1. Now obviously hydrogen doesn't stay as in atomic form, so the reaction can be rewritten as 2 hydrogen molecule reacts with 1 oxygen molecule and form 2 molecules of water. Let me give you another example. Let's say you have glucose molecule, right? Let's say glucose molecule, and when it is completely oxidized in presence of oxygen, obviously it forms 6 molecules of carbon dioxide and 6 molecules of water, right? If a number is not written, that means it's 1. So as you can see here, this complete oxidation of glucose also occurs in a stoichiometric proportion where we have 1 molecule of glucose reacting with 6 molecules of oxygen, right? In biology, throughout the whole lecture series, and you may also be aware already that quantity of anything is of vital importance. Quantity little low, it may not produce the desired effect. Quantity little too high, it may have toxic effect. For example, you know that paracetamol is taken to reduce fever, right? It is used as, the word for it is antipyretic. Okay. Now the general dose is about 500 mg for an adult, a single dose. So if some adult person takes about, let's say, 50 mg, right? Now you know that this is way too less than the standard 500 mg, then it will not have the effect on fever, right? No effect on fever. Okay. On the other hand, if someone takes 1000 mg or even more, then it can have toxic effects. Okay. I'm talking about a single dose, not the dose in a day. Okay. It may have. Let's take another example. You know that in our blood we have glucose, right? Okay. And this concentration on an average is about 90 mg per 100 ml of blood. Now, if by any means, if this amount goes way less, suppose it goes to 50 mg per 100 ml, then someone may feel dizzy, right? You may feel dizzy, you may feel weak. On the other hand, if you have this way too much, let's say 150 mg per ml or even more, then this is equivalent to diabatic condition. Now, even though there is a ratio of reactants, okay, suppose if I want to set this reaction, suppose let me change color, okay, let me change it to blue. Suppose I want to set this reaction, okay. Now I cannot set myself, I cannot pick one molecule of glucose and 6 molecules of oxygen. It's impractical for me. What I can actually do is I can only measure the weight or the volume of the reactants. Okay. So as you can see, like in reality means in macroscopic world, okay, we are able to see only matter, like solid, liquid, gas, but the reactions occur in the, let me change it back to red, okay, reactions happen at molecular level, and which is at a nanoscale level. You cannot literally see it. So we need to find a way, okay, so that we can connect the nano world with the macro world. So what I'm trying to say here is molecules react, okay, at the molecular level, but we don't see molecules. What we see in the real world is matter, right? For example, if you want to set up reaction of glucose oxidation, you can weigh glucose in powder. You will not be able to see the molecule itself. Okay. So let's talk about now stoichiometry means there are some numbers involved of the reactant components. Okay. Now in the macro world, what we have here is we count by seeing, right? You can see in this picture that there are some balls of different colors. We have green, blue, pink. If someone asks you, you can separate out green balls, like this one, this is different shade of green, this, and then maybe one can select pink, this, right? Okay. From this figure itself, you can see that any two balls will have different properties, right? They may have different weight, they may have different shape, and they may have different color. Okay. Now let us take another example, right? Look at this basket of apples. Now any two apples, if you select them, they will have different properties. They may have different weight, right? They have different shapes, taste, color, size, right? Now let's take another example, okay, and here you can obviously see that there are exactly 10 balls. In this particular example, it's slightly different than the previous two examples, this one and this one, that all the properties of each of these balls is identical, unlike the first two examples. Okay, they all have same color, same shape, same size, right? Now this gives us a very powerful application if we want to count something which is of identical in nature. Okay, what we can do is we can count by weighing that. For example, if I ask you that you have to count about 100,000 or 1 lakh balls, right? And you have to count by just see them, okay? Now even if you take about 2 seconds, 2 balls per second, then you will take about 14 hours to count that many balls. That's a long time, okay? Now But the advantage with this set of substance, which is of identical in nature, like each of these balls is identical to the next one, okay, you can weigh out one ball. Suppose a weight of one of these ball is 0.1 gram. Okay, now if I ask you, then weight of 10 power 5, how much 10 power 5 balls will weigh, then you can say, okay, so this will be 10 power 4 grams, right? And that means about 10 kgs. Now this fact itself, this thing, has a very powerful application. What I mean by that is, you weigh one of these balls, and now if someone asks you to count 10 to the power 5 balls, you will simply weigh 10 kg exactly of these balls, and that will have how many? The count will be of 10 to the power 5 or 1 lakh. If someone asks you, okay, so how much, not how much exactly, suppose if someone asks you to count 10 million, right? 10 million means 100 times more than this. That means 100 times more than this will be 1 ton or 1000 kilos. You weigh 1000 kilos of these balls, then you will have 10 million balls, right? It's a simple thing. You just weigh one, weigh the bulk, and you will have exact number of identical substance, whatever it may be. Okay. Now, if you want to have a visual idea how much 1 lakh would be, what you're seeing here is about 40,000 balls. Okay. You can obviously count by, it's a cuboid, well arranged in cuboid. So the point is that we can count by weighing the substance, right? So how about if we apply for our glucose reaction, right? So size of the glucose molecule is in nanometer. So it's impossible for us practically to, unless we use some electron microscope, to see and count glucose molecules, right? Because to give you an estimate how that much is, if you connect, suppose, glucose molecules line to line, right, end to end connection all the way, okay, then if you're seeing this video on a laptop, what you're seeing, this line, the thickness of this line, the thickness, okay, that will have about 1 million glucose molecules if you stack them end to end and in a straight line. Then this thickness of this line will have 1 million molecules. Now, I mean, that itself tells you that how small a molecule is, right? So obviously counting by seeing is not practical, right? So how about we weigh one like we did for the balls, the blue balls, and then how about that? So weight of a glucose molecule is about 180 atomic mass unit. Okay. In your, suppose you confront a question where you don't know what is glucose molecule, but if you are given a formula or you already know the formula, molecular formula, then you can quickly calculate from here, right? You have 6 atoms of carbon. Carbon has an atomic weight of 12. 12 hydrogen atom, each with 1, and 6 oxygen atoms, each with 16, right? So this is 72, this is 12, and this is 96. Total will be 180. Now this is an approximation, not exact, but it will get you in the ballpark. Okay. So if weight of a glucose molecule is 180 atomic mass units and 1 AMU is equivalent to 1.6605 into 10 to the power minus 24 grams, that means each glucose molecule will weigh about that much. That's a very small amount of weight. I mean, it would be difficult to weigh if you have to set up reaction and you need to weigh only one glucose molecule. Okay. Now on the other hand, let's see how much AMU will be contained in 1 gram. So 1 gram is equivalent to 6.022 into 10 to the power 23 atomic mass unit. Right. Now as we see that one molecule of glucose will weigh this much. How about if we take, suppose if I give you this powder, right, and you weigh out 180.15 gram of glucose. Now this numerical value is similar to its atomic weight, but it's in grams. Okay. Now obviously you will do the calculation and you will divide the total weight by weight of one glucose molecule. Okay, and this will give you again 6.022 into 10 to the power 23 molecules. Now this fact is again a very powerful fact, that it has a very powerful application, right? That if you take same numerical value of, suppose the glucose molecular weight was 180.15 AMU. If you take same numerical value, that is 180.15, but in grams of, let's say, glucose, then it will have 6.022 into 10 to the power 23 molecules. Right. Okay. That means whenever you weigh out that much of glucose, you will always have that many number of molecules. Right. So you can do a calculation yourself. Calculate how much, question will be how much magnesium chloride has to be weighed in order to have 12.044 into 10 raised to power 23 molecules. To help you, I'll give you some numbers. Magnesium atomic weight will be 24 and chloride will be 35.5. Alright, so tell me that. Now, this is the core of this lecture, Avogadro's number. It's, in simple terms, is just a name given to this particular number. That's it. Okay. You can have, that means, okay, by the way, this is based on a scientist called Amedeo Avogadro. Okay. That means if you have that many particles of any substance, Okay, then you will have 1 mole particles. So mole is the name given to that number of particles, and this number is called Avogadro's number. Okay, so if I say 1 mole glucose, that means by the way, this Avogadro number has an abbreviation Na. Okay, if you have 1 mole glucose, that means Na molecules of glucose, that means 6.022 into 10 to the power 23 molecules of glucose, and that means if you weigh all these molecules, it will weigh about 180.15 gram. That's the gist of this mole concept. So now look at the usefulness of mole concept. Now what you're seeing is 3 different examples where we have calcium, water, carbon dioxide, obviously solid, an example from solid, liquid and gas. Now if I ask you which of these examples, like first example, second example and third example, has more number of molecular or atomic entities. Now if you know that calcium has an atomic weight of 40 AMU, right? Whereas water has an atomic molecular weight of 18 AMU and carbon dioxide has a molecular weight of 44 AMU. If you look at this numerical value, this is the same what we have taken here. That means that calcium, if you take 40 grams, that is 1 mole. Now 18 ml of water will weigh approximately about 18 gram of water. Again the same thing, that means it is 1 mole of water, and similarly we have 1 mole of carbon dioxide. That means if you take 44 gram of carbon dioxide, that will have same 6.022 into 10 to the power 23 molecules. Same as with this, and same as with this one, right? In case of calcium, it will be atoms, not molecules. Let us practice some questions where we calculate amount of or the number of atoms of calcium present in a glass of milk. We have to start with some approximation. Let's say one glass has a volume of 300 ml, right? And calcium present in milk is about 1 milligram per ml. That means in a glass 300 milligrams, right? So the question essentially becomes how many calcium atoms are present in 300 milligrams of calcium, right? So like we have calculated for previous examples, you have to take weight of substance divided by weight of one atom or molecule, right? So how do we do that? So we'll take 0.3 grams, right, divided by 40 is the atomic weight of calcium, right, and 1 AMU is equal to 1.6605 into 10 raised to power minus 24 grams. Alright. Now when you calculate this, you will get approximately 4.5167 into 10 raised to power 21 atoms. Right. So that many atoms of calcium are present in a glass of milk. Right. Now we can ask another question. If that many atoms are present, or if this much calcium is present in one glass of milk, or the question can be how many moles of calcium is present in a glass of milk, right? So you can calculate from this also. How you can do that? So you have 6.022 into 10 power 23 atoms, that is 1 mole, right? Therefore 4.5167 into 10 power 21 will be how much? So you will have 4.5167 into 10 raised to power 21 divided by 6.022 into 10 raised to power 23, right? So how much will be this? So this will be approximately 0.75 into 10 raised to power minus 2 moles. So that many moles. Okay. Now let's look at another question. How much means in terms of weight EDTA is required to chelate it, right? Now if you are in a younger standard, you might not know what does EDTA do. So to briefly tell you that EDTA stands for ethylene diamine tetraacetate, okay, and it is used to form complex with divalent cations such as calcium or magnesium, right? And suppose you have one EDTA molecule, it will bind with one calcium atom or ion in this case. All right. So coming back to solving our question, how much EDTA is required to chelate it? Now we have 300 milligrams of calcium, right? So does that mean we need 300 milligram of EDTA, right? No, it's not. Okay, so how do we find out that? So there are let's go our standard way. So EDTA has a molecular weight of 292 grams per mole. Okay, so that's the molecular weight of EDTA. Okay, so we have earlier calculated that 300 milligram of calcium has 4.5167 into 10 to the power 21 atoms. That means it will require 4.5167 equal number of molecules of EDTA, right? So we can simply find out how much that many molecules of EDTA will weigh, right? So how do we do that? So we know that 6.022 into 10 to the power 23, that is 1 mole of EDTA will weigh 292 grams. So 4.5167 into 10 to the power 21 molecules, how much they will weigh? You can simply do 292 divided by 6.022 into 10 to the power 23 and you multiply it by 4.5167 into 10 to the power 21. Okay, and when you calculate all of this, you will get about 2.19 gram of EDTA. Alright, so that means to chelate 300 milligram of calcium, you will require 2.19 gram of EDTA. Okay, now let me show you a pro tip. Quickly calculate the same question what we had seen earlier. Okay, to explain you the trick, let me first give you a brief idea. It's just a summary what we have discussed so far. So suppose you have two molecules, right? Molecule A and molecule B, right? And molecule A has a molecular weight of let's say 20 grams per mole, okay, and molecular B has 40 grams per mole of molecular weight. All right, so suppose if I take 20 gram of A, right, and if I take 40 gram of B, then both will have how many molecules? 6.022 into 10 to the power 23, right? No doubt in that. Now if I ask you, let's take 20 gram of A, let's take another example. Let me take like this. Let's not take 20. Let's take 5 gram of A, right? That means this is 1 by 4 moles because its molecular weight of 20 gram. So if you are taking 1/4, that means you are taking 1 by 4 moles or 0.25 moles. Okay. Now if you take, you will need to take how much of B so that it will again have 0.25 moles. So that means you have to do 1 by 4 of this. That means you have to take 10 gram. Right? Now what you are seeing here, there is a relation between these two numbers. Okay? So if you divide this, let me take now blue color. Okay? Yeah. So if you divide this by this, there is a factor of 2. Okay. Now if you want same moles of both again, then you still need to maintain the same factor of 2. Okay. Now let's solve this question. Okay. I'll continue with blue color. Now, how much EDTA is required to chelate 300 milligrams of calcium, right? Now, EDTA has a molecular weight of 292 grams per mole and calcium has a molecular weight of how much? 40 grams per mole, right? And if you calculate the ratio between these two, so how much will it be? 292 divided by 40 will give you 7.3. That will be your ratio. So that means for 300 milligram of calcium, you need to maintain 7.3 factor of weight, because EDTA is heavier, to maintain equal number of atoms or molecules. So if you multiply 7.3 into 300 milligram, that will become how much? 2.19 grams. Okay, you have to practice this before you grasp the efficiency, faster to calculate. Tick. So next time utilize this approach. If you have a question which is like how much something is required to have something else, later on once you start practicing, you will be easily able to calculate if there are more complex questions. All right, let's look at another question. Okay, now let me change color to red. Okay, now you are taking 2 gram of table salt and 2 gram of table sugar, and which one has more molecules, right? Now table salt is what? NaCl, and its molecular weight is 58.44 grams per mole, right? You have to write this grams per mole, okay? Or you can say 58.44 AMU, that is also correct. All right. What about table sugar? So if you are not aware, table sugar is sucrose, okay, and its molecular weight is 342.3 grams per mole. All right. So you can see that this is very different between the two, and if you are taking same weight, right, if you are taking same weight, that means there will be a ratio between these two, and which will be how much? So that means if you take 2 gram of salt and if you compare with 2 gram of sucrose, because of the ratio difference between the two, sugar is heavy, sucrose is heavy. So if you take same weight, it will have lesser number of molecules, right? And how much? It will be lesser by 342.3 divided by 58.44 grams, and the ratio comes to be 5.857. Okay, so 2 gram of salt will have some number of atoms, whatever they are, not atoms, sorry, 2 gram of salt will have some number of molecules. Then 2 gram of sucrose will have about that many times less number of molecules. Okay, all right. Let's look at some example question before we end our discussion. Okay, now the question can be how many atoms are present in present each of carbon, hydrogen, nitrogen, oxygen in 500 milligram of paracetamol. Now that's a structure of paracetamol. Now usually if a structure is given such as this, it's called ball and stick model. Usually it is given that which of the atom is which one, but if it is not, then by default or by convention, hydrogen is labeled as white, oxygen is red, gray is carbon and blue is nitrogen. So from here you can see we have carbon how many? 1, 2, 3, 4, 5, 6, 7 and 8. 8 carbon. Hydrogen how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. Oxygen 2 and nitrogen 1. Okay. And because we are not told the molecular weight, we can calculate based on this molecular formula. So how do we do that? So you calculate, you have 8 carbon atoms, that means you multiply by 12. You have 9 hydrogen atoms, 2 oxygen atoms and 1 nitrogen atom, right? And you calculate all that. Okay. 96, 9, 32 and 14. (151). So the molecular weight of paracetamol is 151 grams per mole. It is also called acetaminophen. Okay, so this is the acid part, that is the amino part, and this is the phenolic group. So the question is this, that is molecular weight, and the question we have is 500 milligram of paracetamol will contain how many atoms of each of carbon, hydrogen, nitrogen and oxygen. Okay, so the first step of the question is how many molecules are present. How many molecules of paracetamol in 0.5 gram, right? So how do we do that? How do we do? You have 0.5 gram divided by its molecular weight and multiply by 6.022 into 10 to the power 23, right? 1.99 into 10 raised to power 21 molecules. Okay. So 500 mg of paracetamol will have that many molecules of paracetamol, and each molecule, the second part of the question, we have split the question into two parts. First we will find how many molecules, that we have found that many molecules, and second how many atoms of CHNO, right? So each of these molecules of paracetamol will have 8 atoms of carbon, 9 atoms of hydrogen, 1 atom of nitrogen and 2 atoms of oxygen, right? That we can get from its molecular formula. So that means number of carbon will be 8 into 1.99 into 10 to the power 21 atoms. Similarly, hydrogen will be 9 into 1.99 into 10 to the power 21 atoms, right? Oxygen will be 2 into 1.99 into 10 to the power 21 atoms, and nitrogen will be 1.99 into 10 to the power 21 atoms. right? You can calculate all this and you will get the answer, right? So I hope you understood the whole lecture. Now let's quickly summarize. So 1 mole molecules means you have 6.022 into 10 to the power 23 molecules. That is the count, the number. And if you take that number of molecule, you will end up with having the molecular weight in grams. That means the weight. So throughout the lecture, we have understood how mole concept help us in counting by weighing. Okay, and if you can extend it to anything, you can have 1 mole of atoms, again NA number of atoms, right? You can have 1 mole of, let's say, electrons. That means NA number of electrons. 1 mole of apples. That means NA number of apples. There will be a lot of apples though. Alright, so we are ending the lecture and I have some practice questions for you which you can do on your own. So the first question is, if you drink 4 liters of water every day, how many molecules of water you are intaking through drinking? That's an easy one. If all the molecules of 18 gram of glucose are converted into maltose, how many maltose will be formed? Now let me give you some idea. So glucose molecule, okay, 2 glucose molecules, they add up, okay, and they form maltose and 1 molecule of water, right? And if you want a formula, actually I will not give formula, you can calculate the formula from the glucose molecular formula which I had given earlier in the lecture. Okay, you add up both and then you remove this, you will get the formula for this one. Okay, now you have this total as 18 gram. Okay, then how much maltose will be formed? Okay, that will be your question. It's a good question. Okay, practice this one especially and let me know in the comment section. We will cover this up in the next lecture. How many moles, and the third question is, how many moles of water are present in 1 liter of pure water? That's a good question because it will tell you that if you have pure water, it still have a molar concentration, and that will be topic of our next lecture. What are concentration terms? It can be moles, molar concentration, then we have normality, we have weight, percentage. Okay, we will cover that all in the next lecture. All right, stay safe, have fun, bye bye.